All right. The main reason I'm here today, this morning, is because in the recent month, actually in the recent years, my students and I have spent way too much time looking at and writing recursive common table expressions or recursive CTEs in SQL. That's a particularly ugly syntactic construct in SQL, but it's very super useful. Really bounce off the expressiveness of SQL. What you can do here, you can initialize query Q1 and then you can iterate this query Q loop as many times as needed. And what you get there is actually Turing expressiveness in SQL. So that's actually a very, it's an odd man out construct in the language, but it really is the core of our attention for, has been the core of our attention for the recent years. And if you show this to students, they normally are excited. What can you do with that? And then you tell them, man, this computes the fixed point of this particular query. And then they say, yeah, right, oh, fixed point, let me think. That sounds complicated, right? And then you would say, well, it might sound complicated, but the fixed point semantics of SQL, of the CTEs, they really serve SQL well. If actually, if it's semantically sound, so if the Q loop query is just monotonic, then you're right, you're guaranteed that such a fixed point will be unique. And if Q loop is monotonic, then you can employ clever evaluation techniques like the semi-native evaluation to evaluate these recursive CTEs efficiently. And that might not mean much to many folks out there, but this monotonicity business and the semi-native evaluation business actually has some consequences out there that gave us some headaches in recent months and years. So monotonicity is actually a syntactic restriction that database systems enforce on the Q loop part of your recursive CTE. There's a certain set of constructs that are now disallowed in the Q loop part. And some of these may be acceptable. Some of these, like grouping or aggregation or grouping aggregation, are actually forbidden in the Q loop part because they would ruin the monotonicity of Q loop. They can really hurt you. And everybody out there who spent some time with recursive CTEs knows some workarounds. You move computation in and out of the CTE, try to avoid grouping aggregations. There's a lot of workarounds, endless blog articles about this out there. But what you end up with is normally it's a semantic and syntactic nightmare. What you end up with. That's really a shame. Semi-native evaluation really boosts the efficiency of the evaluation of such recursive CTEs, but they have a very dire consequence. When you evaluate the iterative part of the recursive CTE, what you see is not the history of the entire computation or the iteration that you've done. What you see is just the most recent iteration that you've just performed. Everything else is forgotten. It will be part of the result of the CTE, but your current Q loop iteration cannot see that. It has no history, no memory of the computation that has been done. So what people are doing, they're doing workarounds. So they are constructing tables T that have some interesting payload in them. That may be in these few first columns, but they may also construct additional auxiliary history columns in which they try to remember the history of the computation, maybe some nodes that you visited during graph traversal and so on. And what you see is that this history of the computation that you try to accumulate really accumulates and really hurts your efficiency in the evaluation of these queries. So more workarounds. That's really tough and really bad. And what you see out there is that the excitement for recursive CTEs quickly wanes, and then people say, okay, so if there is any recursive, iterative, or computationally more complex job I have to do in my queries than or with my data, then I'd rather do that outside the database system, not using SQL, and I'd rather use Python or anything else. All right. In the coming minutes, I would like to take a different view of the recursive CTE. That's the non-recursive CTE at the top, and I would look at these CTEs in terms of the operational semantics, or the very simple loop-based computation that is being performed by this particular SQL construct. Here you can see that there's actually some iteration going on, and Q loop is placed inside this loop. This is really iterated. This query is iterated and it sees this table W. This is actually the result of Q loop that has been performed in the iteration just before. Okay, so this would compute the fixed point semantics of the with recursive, given that Q loop is monotonic. But of course, this is just an iterative computational pattern, and it will be useful, and it's easy to understand actually, even if Q loop is not monotonic. It's just some iterative computation with some well-defined exit condition at this point. I will also use this graphical representation of the same loop. It just says the same thing. We have this particular loop in computation. Q1 is doing its job once, and then Q loop is doing its job many times, seeing its formal results, submitting all of the intermediate results to this union table U, where everything is aggregated, and this will be the final result of the computation. But as you can see, there's a brick wall here. Q loop will never be able to see the history of the computation. It will only ever see its immediate prior results. That's how recursive CTEs work. And if you look inside the engine internal, the database kernel internal implementation of recursive CTEs, what you will find there, at least I see it if I take off my glasses, then I see some computation pattern that mimics this. This is actually what happened inside the actual engine internal implementations out there. So, well, of course, this particular loop, you've seen it before, is not cast in stone. There have been people in this room, actually people from Munich in 2017 who said, well, that's all well, but this is not set in stone. We can tweak that, we can modify that. And actually, this would be their modification. They take stuff away. You see that in this particular change construct, it's called with iterative, not with recursive. In this construct, there is no union table. There's no collecting of history information. In their particular use case, they didn't need this collect history information. You cannot access it anyway. So why bother initializing it and maintaining it? Just throw it away. What you end up with is just this core of the iterative computation. The result of this computation would be the last non-empty result that Q loop has computed for you. This is with iterative as proposed by the good people from Technical University of Munich. And we said, that's actually a nice approach. Let's take this operational semantics and tweak it. Let's see how we can improve it, how we can change it, how we can adapt it to arrive at different iterative or recursive, if you will, SQL construct that can do something good for us. We will keep the simple loop-based CTE or recursive CTE behavior as before, also because we want to leverage the existing infrastructure inside database kernels to evaluate our new iterative constructs. But we tweak their behavior. In the coming few minutes, I would like to sketch two deviating behaviors that we're proposing in this particular paper. One in which the intermediate results that your Q loop query emits is kept in the key dictionary, a key dictionary that actually your Q loop query can access, so it can see the history of computation, but it's not a dictionary, or it's not a dump of stuff that we add to, but it's a key dictionary in which we can selectively update the results that we've produced before. So we have the opportunity to update what we've computed before. And I will show an example why that might be useful. And there's a different version, the with iterative TTL. TTL stands for time to live variant, in which Q loop can see its earlier results unless they are too old. Results that you have produced can be seen again by Q loop unless they're too old and they expire. So they don't pollute your intermediate results that Q loop will see in subsequent iterations. So that would be the original Q loop, the original semantics of recursive CTE. That would be one of the modifications that we proposed, the key dictionary variant. And if you can see here, unlike in the original variant where we just dump all the intermediate results that we've seen onto U, we use the new intermediate results to update, to upsert U, and to obtain an updated version of these results. And as you can see here, Q loop indeed can read, if it likes, it can read these updated version of these intermediate results. All right. So that would be the new picture here. Everything remains the same. It's just this looping computation. And if you like, using this syntactic modifier recurring, if you like, QLoop can also refer to the intermediate results that are maintained here using an upsert operation. An upsert operation that behaves just like you probably expect it to behave. Right, so QLoop has access to everything that has been just computed before, but also if it likes the history of the computation. It depends on the keys that you use to insert in this dictionary, how large this dictionary will grow. There's some control over the size of the dictionary. And what you can see is if you start to program with this particular variant of the recursive CTE, then you will find yourself programming in a somewhat imperative style, just like in imperative programming language that you know and love. We have implemented one example of an algorithm where you try to find the connected components of an undirected graph. Then what we would like to have is to assign every node its particular component it lies in. So these two nodes lie in component C0. We would like to compute an array and an assignment of nodes to their components. And there's a folklore algorithm out there that works in an iterative fashion where you first assign each node its own component, and then you look at your neighboring nodes and you see that your neighboring node is in a smaller component than yourself. Then you assign yourself to that particular new component. There's some destructive update here in this imperative style algorithm. And if you iterate that, then you end up with the final assignment of nodes to connected components. If you look at the left-hand side of this slide, just at the left-hand side, then this is the folklore imperative style algorithm to compute the connected components. And I've shown you the with iterative key variant of this particular algorithm, in which we indeed have a node to component dictionary that we are iteratively updating in this particular query. And if you look closely, you can draw connections from the imperative style code directly to all the clauses in the recursive CTE here. And it's a very nice way to think about recursive iterative programming in SQL that comes close to stuff that developers out there can understand and love. Right? And you also get rewarded because you save space in these ever-growing tables. You don't need these ever-growing tables. You control the size of these tables. I would like to skip over this performance slide. Actually, I'm much more excited about the style in which you can express iterative computation than really second counting here. Okay. There's a second variant of iterative CTE that we are proposing. This again is the old recursive SQL CTE. This would be the new style in which we have aging row memory. And I would like to draw your attention to this particular new table R, which contains rows that you have just produced. This is the stuff that you've just produced, and stuff that you remember, but it slowly expires. The query QLoop is in control over when a row expires, how long it will be current. And here you can see how stuff that we would like to remember is being remembered, but is slowly expiring. When the rows are not yet expired, the QLoop query can selectively recall this older knowledge and can access it during its computation. Right, so we have, thank you, George. This is selective row memory. And what you can do with that, for example, is implement very succinct, very elegant parsers in recursive SQL. Right, so that would be a grammar, a context-free grammar in Chomsky normal form. It's very easy to have a tabular representation of that. And if you have that tabular representation and you use this query I will be showing you in a few seconds, then you will see it will use that grammar to perform a bottom-up parse of some input string that you give it. The bottom-up parse, some parsing knowledge will be found in iteration 0 of our CTE. Some will be in iteration 1, 2, 3, and so on. This will proceed bottom-up. But if you look at this particular node at iteration 4, you can only establish this particular node at iteration 4 if you can remember all the knowledge that you have already found at iteration 0. It's not enough to just remember the knowledge that you found in the immediate iteration 4. This with iterative TTL gives you a very elegant, very simple way to remember what you've done many iterations ago. This would be a complete parser. This would be a complete parser for context-free grammars with iterative TTL. You see that we are referring to older parsing knowledge here. We can do this in a nonlinear fashion. I can talk about this afterwards why this makes sense in this particular case. And as you can see, we have full control over the time to live. How long do we want to recall all the parsing results? At some point, we may forget them, but we may not forget them too early. So this would be a context-free parser in 8 lines of SQL. And it behaves great. But George tells me I cannot tell you about how great it behaves. And this is the last slide. There's, of course, variants of iterative CTEs that we can imagine now. Once we get rid of this monotonicity in fixed point cage, when we get rid of that, we can imagine having multiple working tables, multiple tables W that I showed you. Or we can have tables that reveal their older knowledge, the knowledge that we have acquired, not in a table-like, but in a queue-like or a set-like fashion. Or we can imagine with recursive constructs or with iterative constructs that we have designed just to serve as back-end languages, as target language for the compilation of other languages, for example, PSQL. And like 3 years ago, I talked about this at CIDR. We're still working on that, and it's still lots of fun. Thank you so much.